It's funny how our bodies can completely trick us.
Oh, absolutely.
Like, especially when we rely on our senses to tell us absolute truths about the world. Think about this scenario for a second. You wake up on a freezing winter morning and you walk into your kitchen barefoot.
I can feel the cold already.
Right. So half the kitchen floor is covered in a nice, thick wool rug, and the other half is bare slate tile. You step on the rug, and you feel totally fine. Then you take one step over onto the tile, and you immediately flinch.
Yeah, your brain just screams that the tile is freezing cold.
Exactly. But here's the crazy part, right? The part that you probably know intellectually, but your nervous system just refuses to accept in that split second. The rug and the tile are the exact same temperature.
Yep, they've been sitting in the same house in the exact same ambient air all night long.
It's just wild to think about.
It's actually one of the greatest illusions of human biology. I mean, we walk around assuming our skin acts like a thermometer, giving us an absolute reading of the environment.
But it doesn't.
No, not at all. We don't actually have thermometers embedded in our skin. What we have are heat flow sensors. Biology didn't equip us to measure absolute temperature. It equipped us to measure the rate at which thermal energy is entering or leaving our bodies.
Which makes total sense from a survival standpoint. You need to know if you're losing heat too fast.
Precisely.
So when you step on the tile, your foot isn't feeling the temperature of the slate. What you are feeling is the staggering speed at which the thermal energy is being ripped out of the molecules of your skin and pulled into the floor.
Yes, and the rug, on the other hand, just sort of traps the heat right there against your foot.
And this illusion, it gets magnified to an extreme degree when we start interacting with metals.
Oh, without a doubt.
You touch a piece of steel railing outside in the winter, or you grab a copper pipe in your basement, and it gives you that instant, shocking chill. It feels infinitely colder than, say, a piece of wood sitting right next to it in the exact same environment.
Because the heat is just rushing out of you.
Right. And that everyday phenomenon brings us to the core mystery of our deep dive today. We're going to look way under the hood of reality. We're zooming down into the microscopic, hidden infrastructures of heat transport inside solid objects.
It's a fascinating area of physics.
It really is. Because when you look at the raw physics of how heat moves, there is a paradox that is absolutely mind-bending once you start to unpack it.
It really upends everything we intuitively assume about materials. I mean, we categorize the physical world into neat little boxes, things that conduct energy and things that block it.
But the universe doesn't actually care about our boxes, does it?
Not even a little bit.
So let's lay out the paradox using copper as our starting point. Copper is, it's the absolute poster child for conduction. We've essentially wired our entire global civilization with it.
For good reason.
Yeah, it conducts electricity like a dream, with almost zero resistance, which is why it's in the walls of the room you're sitting in right now.
Yeah.
And intuitively, it also conducts heat incredibly well. Like, if you want a top-of-the-line frying pan, you get one with a thick copper bottom, because the heat from the stove element spreads out across the pan almost instantly. Copper is the gold standard for moving energy from point A to point B.
It is the baseline against which we measure almost every other conductive material.
But then, you turn around and look at diamond. Now, diamond is an insulator. If you try to run an electrical current through a diamond, absolutely nothing happens.
It is a brick wall to electricity.
Total brick wall. It holds its electrons in a vice grip. But if we look at the lab data from the solid-state physics research we're diving into today, diamond conducts heat 5 times better than copper.
5 times? Let that sink in.
It's staggering. A material that entirely blocks the flow of electricity is somehow 5 times faster at moving heat than the ultimate universal champion of electrical conduction.
It really feels like a glitch in the physics engine of the universe.
It does. If conductivity is a fundamental property of a material, how can diamond be so utterly terrible at moving one form of energy and the undisputed heavyweight champion of the universe at moving another?
Well, to solve that, we have to recognize that heat and electricity aren't always taking the same highway. The research we are analyzing today frames this perfectly.
Yeah, I love how they put it.
It describes 2 completely different infrastructures, what the authors brilliantly call the 2 major political parties of heat transport.
And our mission for this deep dive is to unpack both of those parties. On one side, we have the chaotic, massive sea of free electrons that governs metals like copper.
And on the other side?
On the other side, we have the highly disciplined, purely quantum world of phonons that rules insulators like diamond. We're going to translate these incredibly dense laboratory-level physics concepts, things like the Boltzmann transport equation, crystalline harmonicity, and clap scattering into a mechanical picture you can actually visualize.
We promise it won't be as scary as those words sound.
Definitely not. By the time we're done, you'll understand exactly how heat is secretly moving through the objects you touch every single day, and we'll have solved the mystery of diamond's ultimate thermal supremacy.
But to truly appreciate the genius of how diamond operates, we have to start with the baseline. We need to look inside that copper wire or that copper pan and observe the tiny workers that are physically carrying the heat away from your hand.
Right. We have to understand the rule before we can marvel at the exception.
Exactly.
So let's get right into the microscopic architecture of metal. When you press your hand against that copper pipe and it feels instantly cold, what is mechanically happening down at the atomic level? I know we talk about atoms being these rigid building blocks, but metals do something really weird with their outer layers, don't they?
They do. Metals are incredibly generous on an atomic level. In most materials like plastics or wood or ceramics, atoms hold on to their outer shell electrons very tightly. They are bound locally.
Okay, so they're stuck.
Right. But in a metal like copper, the atoms essentially surrender their outermost electrons. The copper atoms arrange themselves into a rigid, positively charged grid. We call this the crystal lattice.
Okay.
And all those detached outer electrons are simply allowed to slosh around freely between the atoms. This is what physicists refer to as the sea of free electrons, or an electron gas.
I always found the gas analogy fascinating. We're talking about a solid piece of metal, something you can bang on with a hammer, but inside of it, the electrons are behaving like the air molecules floating around in a balloon.
Yeah, it's a great mental image.
They aren't tethered to any specific nucleus. They form a communal pool that belongs to the entire piece of metal.
That communal pool is the key to everything metal does. Because those negatively charged particles are untethered, they are free to roam anywhere within the boundaries of the object.
So they can just go wherever.
Precisely. Now, we have to bridge the gap between this microscopic picture and the macro world concept of heat. When we talk about heat, we aren't talking about a magical, invisible fluid. We are talking purely about kinetic energy. We're talking about motion.
So when my warm hand touches the cold copper, the heat from my hand is actually just the frantic physical vibration of the molecules in my skin.
And that furious vibration literally smashes against the surface of the copper. It transfers that kinetic energy, that physical jolt, directly to those free electrons floating right near the surface of the metal.
And because these electrons aren't tied down, they don't just sit there and vibrate in place like the atoms in a piece of wood would.
Right.
They take that energy from my hand and they run with it.
They zip away from the surface, carrying that kinetic energy deep into the cold interior of the copper. And the speeds we are talking about are difficult for the human brain to process.
How fast are we talking?
Well, in physics, we measure this using something called the Fermi velocity. We are talking about speeds on the order of 1,000,000 meters per second.
1,000,000 meters per second, that's what, thousands of miles per hour?
Millions of miles per hour, actually.
Wow. No wonder the heat feels like it's being ripped from your skin. It's being loaded onto vehicles moving at 1,000,000 meters per second. I was trying to picture this while going through the source material.
It's hard to visualize.
Yeah, but if you imagine the interior of that copper wire as a country, these free electrons are like a massive, chaotic fleet of delivery trucks.
I like that analogy.
But they aren't driving on an organized highway system with painted lanes and traffic lights. They're just driving off-road, completely unbound, everywhere all at once, carrying this cargo of heat at absolute breakneck speeds. It is pure, unadulterated chaos.
The sheer volume of those delivery trucks, coupled with that Fermi velocity, is the fundamental mechanism of a metal's thermal conductivity. In our equations, we denote this specific type of heat transfer heat moved by electrons as kappa sub E.
Kappa sub E. Okay, now, here is where I want to push on the history a bit, because our sources highlight one of the most elegant laws in solid-state physics, the Wiedemann-Franz law.
Oh, it's a beautiful piece of science.
It really is. And I was looking at the timeline, and Wiedemann and Franz published this law in 1853. But J.J. Thomson didn't even discover the electron until 1897.
Right. Decades later.
So how on earth did two scientists in the 1850s figure out the relationship between heat and electricity in metals without even knowing that the delivery truck itself existed?
That is the beauty of empirical science. Long before we had the quantum mechanical model, scientists were measuring macroscopic properties. Wiedemann and Franz meticulously measured the thermal conductivity and the electrical conductivity of various metals.
Just doing the grunt work in the lab.
Exactly. And they noticed an undeniable universal pattern. They realized that in any metal, if you take its ability to conduct heat, its thermal conductivity, kappa, and you divide it by its ability to conduct electricity, its electrical conductivity, sigma, that ratio, is directly proportional to the absolute temperature.
So kappa divided by sigma equals some constant multiplied by the temperature.
Yes,
And it didn't matter if they were testing iron or silver or copper. The ratio always held up.
always. And the profound implication of that ratio, which they observed empirically but wouldn't fully understand mechanistically for another half-century, is that the exact same mechanism must be driving both phenomena.
It's the same trucks.
Yes, it proves that the free electrons that carry the electrical current when you plug your TV into the wall are the exact same free electrons carrying the thermal energy when you heat up a pan.
They're moonlighting. The electric company and the heating company are literally the exact same particle.
That's a great way to put it.
And because it's the same mechanism, a material that is a great electrical conductor is automatically, inextricably, a great heat conductor. You literally cannot have one without the other in a metal. Nature tied them together.
And nature tied them together with mathematical precision. You mentioned the equation. Kappa sub E over sigma equals L times T. That constant L is known as the Lorentz number.
Okay, the Lorentz number.
Yeah, and when scientists finally developed the Drude-Sommerfeld model in the early 20th century, which is the model that treats these free electrons as a quantum gas, they were able to theoretically derive that Lorentz number.
I want to linger on this derivation for a second because the source material points out how incredibly pure this number is. It's not just some random messy fraction that scientists measured in a lab and accepted, right?
No, not at all.
When you strip away all the complex variables of this specific metal, when you cancel out the mass of the atoms, the density the electrons see, the physical dimensions, we're left with an equation for L that is made up entirely of fundamental constants of the universe.
It's truly amazing. The equation is L equals pi squared over 3 times the Boltzmann constant over the elementary charge squared.
Let's break those ingredients down because it almost feels philosophical. Pi is obviously the fundamental ratio of the circle's circumference to its diameter, a pure geometric truth. The elementary charge, E, is the fundamental electric charge of a single electron. And the Boltzmann constant. I always found the Boltzmann constant fascinating because it's essentially the translator between the microscopic and macroscopic worlds, right?
That's exactly what it is.
It links the temperature we feel on a macro level to the average microscopic kinetic energy of particles.
That's a great way to describe it. It's the bridge. So when you put those fundamental building blocks together, you get L, which is approximately 2.4 times 10 to the negative 8 watts ohms per Kelvin squared.
It's just a pure number.
Exactly. The point the source material is making is that this isn't just a number. It's a structural pillar of reality. It tells us that the electron gas behaves according to strict, elegant rules, no matter what kind of metal it's trapped inside.
It is beautiful.
Yeah.
But looking at all of this, the million meters per second Fermi velocity, the massive communal pool of electrons, it raises an obvious mechanical question. If these electrons are zipping around at millions of miles an hour carrying heat, why isn't copper infinitely conductive? Why does it take any time at all for a copper pan to heat up? There has to be a speed limit. Something must be acting as physical resistance.
You're right, and to find the resistance, you have to look back at the environment the electrons are driving through. We have the delivery trucks, and we have their incredible speed. But they are not driving in a frictionless vacuum.
Right, because there are atoms in the way.
Exactly. Remember, the metal is made of a rigid grid of positively charged atoms. And because the metal is sitting at room temperature, those atoms aren't perfectly still, they're vibrating.
Okay.
On top of that, no metal is perfectly pure. There are missing atoms, extra atoms squeezed in, or atoms of different elements disrupting the perfect grid.
So if we return to the delivery truck analogy, it's like sending a million trucks off-road at top speed. But the terrain is completely littered with boulders, and the ground itself is violently undulating like an earthquake.
That is exactly what they face. As the incredibly fast electron tries to carry its heat cargo across the metal, it inevitably crashes. It smashes into a vibrating copper atom, or it deflects off an impurity.
So they can't just go in a straight line.
No. In physics, we call these crashes scattering. Every time an electron scatters, it ricochets in a random direction. It loses its forward momentum. It drops some of its heat cargo. It has to recover, accelerate, and start moving again until the next inevitable crash.
That relentless scattering is the absolute limit of metallic heat conduction. The electrons are trying to force the heat through using sheer, overwhelming brute force. But the environment is incredibly hostile to any kind of straight-line movement.
It really is.
It's an aggressive, chaotic, highly inefficient way for an individual particle to travel. It only works because there are simply so many of them.
That is the perfect summary of the metal paradigm. The massive, chaotic sea of electrons fighting against a vibrating environment. But knowing this sets us up for the pivotal shift in our source material.
Right, because if this sea of electrons is the ultimate mechanism for moving heat, we run headfirst into a massive problem when we look at the rest of the periodic table.
Yes, we do.
What happens if a material does not have any of these electron delivery trunks? I mean, literally zero. How can it possibly move heat? If you look at a diamond, or a ceramic mug, or a glass window, they are insulators.
Their electrons are locked down.
Exactly. Their atoms lock up their outer electrons tightly in chemical bonds. Nothing is free to slosh around. Yet, if you pour boiling water into a ceramic mug, the outside of the mug gets hot in seconds. The heat moves, without a single free electron to carry it.
How? This is where we completely discard the delivery truck analogy. We're entering the domain of the second political party of heat transport, the phonon phenomenon. To understand heat in an insulator, you have to wipe the slate clean.
Okay, my mental slate is wiped, no electrons, just atoms locked in a rigid grid.
Take the picture for me. How does heat move if nothing is allowed to leave its station? Imagine the atoms in a solid, non-metallic crystal, like our diamond. They are arranged in a perfect, repeating, three-dimensional geometric pattern. But they aren't just floating next to each other.
They're chemically bonded.
Yes. You can visualize these bonds as tiny, invisible springs connecting every atom to all of its immediate neighbors in the grid. Now, what happens if you take a blowtorch to one side of this crystal lattice?
Well, the heat from the blowtorch is kinetic energy, so the atoms on that side are going to start jiggling. They're going to vibrate violently.
But because they are connected by those springs, an atom cannot vibrate in isolation. When the first atom jiggles, it stretches and compresses the spring, which physically pulls and pushes on the adjacent atom, forcing it to jiggle.
Oh, I see.
And that atom pushes on the next one. What you generate is a continuous wave of mechanical vibration that propagates through the entire crystal lattice.
It's like a ripple expanding across a pond, but the medium is made of jiggling carbon atoms instead of water molecules.
Yes. Now, here is where solid-state physics takes a conceptual leap that is so weird and brilliant that it almost borders on magic.
I'm ready.
Dealing with the complex mathematical thermodynamics of trillions of individual atoms jiggling and pulling on trillions of intersecting springs is computationally impossible. So in the early 20th century, physicists applied the rules of quantum mechanics to these vibrations.
Okay, quantum mechanics.
They realized that a wave of vibration in a lattice can only have discrete, specific amounts of energy. It is quantized. And because it's quantized, physicists can mathematically treat that wave as if it were a distinct physical particle moving through space.
Wait, so they take a verb, the act of vibrating, and mathematically dress it up as a noun, a particle.
They do. They call it a quasi-particle.
Yeah.
And they gave this virtual particle a name, a phonon.
A phonon. Like a photon, which is the particle of light, but a phonon is the quantum particle of sound or mechanical vibration.
Precisely.
The analogy that always clicks for me here is a massive sports stadium.
Oh, the wave analogy.
Yeah. Imagine a packed stadium, and someone in the front row stands up, throws their arms in the air, and sits down. The person next to them does it a fraction of a second later, and so on. Suddenly, you have the wave traveling all the way around the arena.
We've all seen it.
Right. And if you are watching from a blimp above the stadium, you clearly see a thing, the wave moving at 20 miles an hour around the circle. But if you look closely at the individuals, not a single person actually moved from their assigned seat. They just stood up and sat down in place.
They didn't go anywhere.
The people are the atoms. The wave is the phonon. The energy and the pattern travel seamlessly, even though the physical matter stays exactly where it is.
I love that analogy because it perfectly captures the dual nature of it. Just as you can measure the speed and the kinetic energy of that stadium wave from the blimp, physicists can measure the speed, energy, and momentum of a phonon.
Even though it's not a real object?
Right. It isn't a physical particle like an electron or a proton, but it behaves in our mathematical equations exactly like a real particle carrying a discrete package of heat energy across the crystal.
So in an insulator, the heat is not being thrown onto a tiny delivery truck. It is being transmitted through the very structure of the material itself, passed along spring by spring as a continuous wave of physical vibration. It is quite literally a microscopic stadium wave of heat.
And our source material provides us with the mathematical framework for how efficient the stadium wave is. They borrow principles from the kinetic theory of gases. The formula for the thermal conductivity of an insulator, which is entirely powered by phonons, is kappa sub P equals 1/3 C times V times L.
Okay, let's break this down. Kappa sub P is the phonon conductivity. We have three variables dictating how well the wave moves: C, V, and L. If I'm looking at this logically, C stands for a specific heat capacity.
Correct.
Conceptually, that must be a measure of how much thermal energy those microscopic atomic springs can absorb and hold at a given temperature, right?
You're hitting on the core of it. Specific heat is essentially the capacity of the system. How much energy is required to make the lattice jiggle to a certain degree? A higher capacity means the phonon wave can carry a larger package of heat energy as it propagates.
Okay, so the size of the payload. Next is V, the velocity. Now, because a phonon is fundamentally a wave of mechanical vibration traveling through a solid, does that mean its velocity is just like the speed of sound through that specific material?
It is exactly the speed of sound. Sound, as we hear it, is just a macroscopic low-frequency lattice vibration. Heat is a microscopic high-frequency lattice vibration.
Wow.
But the underlying physics of the wave propagation is identical. They travel at the same fundamental speed dictated by the material.
That is wild. I mean, we separate acoustics and thermodynamics in our heads, but at the atomic level, they're using the exact same infrastructure.
They really are.
Okay, so we have the capacity of the springs, which is C, and the speed of the wave, which is V. What is the last variable, L?
Well, LNS stands for the mean free path. We talked earlier about how the electron delivery trucks in metal were constantly crashing into things. Well, phonons crash too. The mean free path is simply the average physical distance the phonon wave can travel before it crashes into something and scatters, losing its forward momentum.
So the total heat conduction of an insulator is a product of how much heat the wave holds, how fast it travels, and how far it can go before it gets disrupted. That is incredibly elegant.
It sums it up beautifully.
But before we pit this phonon wave against the electron C to see why diamond wins, there is a nuance in the sources that I think is crucial. We said insulators only use phonons because they have no free electrons. But what about metals? Don't metals have atomic grids that vibrate too?
They absolutely do. Copper has a crystal lattice of vibrating atoms, therefore copper has phonons. Every solid object above absolute zero has phonons. Metals have both infrastructures operating simultaneously in the same space.
Wait, really? So inside a copper wire, you have the chaotic electron delivery trucks zooming around, and D, you have the stadium wave of phonons propagating through the grid at the exact same time.
Yes. But here's the catch that explains why we usually ignore phonons in metals. The electron transport kappa sub E is so overwhelmingly powerful, the electrons are so densely packed and moving so incredibly fast that they completely dominate the thermal conductivity.
Oh, I see.
The heat carried by the phonons in a piece of copper accounts for less than a few % of the total heat transfer. It's essentially a rounding error in the engineering calculations.
It's like having a raging, massive river, and right next to it, a tiny trickle of a stream. They're both moving water down the mountain, but the river is doing 99% of the work. You don't even notice the stream.
Exactly. But in an insulator like diamond, the river has been completely dammed up. There is zero electron flow. Suddenly, that tiny trickle of a stream the phonons has to take on 100% of the responsibility for transporting the heat.
Which brings us back to the central paradox of this whole deep dive. We've established the formulas. We know diamond relies entirely on the jiggling of atoms. We know copper relies on a massive sea of superfast electrons.
Right.
So how does the invisible jiggling wave in a diamond not just beat, but absolutely annihilate the superfast sea of electrons in copper?
The raw numbers from the lab really force you to reconsider what makes something a good conductor. Copper's thermal conductivity is about 400 watts per meter Kelvin. That's fantastic. That's why it feels cold inside.
400, okay.
But diamond's thermal conductivity is roughly 2,000 watts per meter Kelvin. It's a blowout. And the secret lies entirely in two of the variables in our phonon equation: V, velocity, and L, the mean free path. The source material notes that in a diamond, these two parameters are pushed to what the authors describe as the strongest level in the universe.
The strongest level in the universe.
Okay.
Okay, let's unpack the first parameter, velocity. We just established that the velocity of a phonon is the speed of sound through the material. So what dictates the speed of sound? If I tap on a piece of lead, the sound is kind of a dull thud. If I tap on a piece of glass, it rings sharply.
Right, the wave travels differently.
Obviously, the mechanical wave travels differently based on what the object is made.
The speed of a mechanical wave through any solid depends fundamentally on two things: the mass of the atoms and the strength of the chemical bonds connecting them. Think of our spring and weight model.
Okay.
How fast a vibration travels depends on how stiff the springs are and how heavy the weights attached to those springs are.
So let's look at diamond's atomic makeup through that lens. Diamond is pure carbon, nothing else. Where does carbon sit on the periodic table regarding mass?
Carbon is quite light. It's atomic number 6, so you have a relatively low mass. That's the first advantage. Lighter objects are easier to accelerate. They respond to the push and pull of the springs much faster than heavy atoms like lead or gold.
So we have extremely light atoms. What about the springs?
The carbon atoms in a diamond undergo what chemists call speak-3 hybridization, forming rigid covalent bonds. In 3 dimensions, each carbon atom locks into a tetrahedral structure with its neighbors.
Okay, tetrahedral structure.
In the world of atomic physics, the carbon-carbon covalent bond in a diamond lattice is one of the tightest, stiffest, most unforgiving bonds in all of nature.
So we have extremely light atoms connected by the stiffest springs in the universe. The analogy that jumps out at me here is tuning a guitar string. If I want a guitar string to play a very high, fast note, meaning the vibration of the pluck travels back and forth along the string incredibly quickly, what are my two options?
You adjust the string.
Right, I can buy a thinner, lighter string, and I can turn the tuning peg to pull that string under immense tension. If I have a feather-light string pulled perfectly tight, the moment I pluck it, that vibration shoots from one end to the other almost instantaneously.
That is an excellent mechanical visualization. Diamond is the ultimate tightly tuned guitar string of the microscopic world. Because of this rigid, lightweight structure, the phonon doesn't just meander through the lattice, it tears through it.
Fast.
The speed of sound inside a diamond RV parameter reaches a staggering 18,000 meters per second.
18,000 meters per second. To put that in perspective, sound travels through the air we're breathing right now at about 340 meters per second. So a wave of heat inside a diamond is moving more than 50 times faster than the sound of my voice reaching the microphone.
That's Mach 52.
Mach 52.
It is among the highest sound velocities of any known material. So right out of the gate, in our equation, kappa equals 1/3 C times V times L, the V parameter for diamond is astronomically high. It is pushing the thermal energy at an incredible speed.
But speed is only half the battle. Anyone who's driven a sports car in a major city knows that speed doesn't matter at all if you're constantly stuck in traffic or crashing into brick walls.
You're not going anywhere fast.
Right, you can have a Ferrari, but if you're driving in downtown Manhattan at rush hour, a guy on a bicycle is going to beat you to your destination. Which brings us to the most critical variable in the entire equation, Nile, the mean free path. We need to talk about what actually stops a phonon, what acts as the invisible brakes inside a solid material.
This is where we dive into the deep physics of thermal resistance. In our metal analogy, the electrons crashed into physical impurities and vibrating atoms. But a phonon isn't a physical particle, it's a wave of energy. What does a wave crash into?
Yeah, what does it hit?
The answer is it crashes into other waves. The thermal resistance in an insulator is caused by phonons colliding with other phonons.
I mean, I understand wave interference on a basic level.
Right.
If you drop 2 pebbles in a pond, the ripples move outward, and when they intersect, they create a momentary peak or valley where the energies combine. But how does that stop the heat from moving forward?
It depends entirely on the nature of the collision. Inside a heated crystal lattice, there are trillions of phonons moving in all different directions, carrying different amounts of thermal momentum. Okay.
When these phonon waves intersect and interact, they scatter. But the physics of these collisions plays out in 2 completely different ways, and only one of them actually throws the car in reverse.
Let's break them down. The source material refers to the first type as the N process, or normal scattering. What exactly happens in a normal collision?
In an N process, 2 phonons crash into each other and merge into a new phonon, or they scatter off each other. But the crucial rule of physics that is maintained is the conservation of total momentum.
So they keep moving.
Right. If phonon A is generally moving to the right and and phonon B is generally moving to the right, and they collide, the resulting wave energy is still fundamentally moving to the right.
It's like two billiard balls hitting each other on a felt table. They smack together, maybe they deflect a few degrees off their original paths, but the overall forward kinetic energy of the break is still moving powerfully across the table toward the opposite pockets. The energy doesn't stop, it just reorganizes itself. Exactly. Because the forward momentum is completely conserved, an end process does not actually slow down the overall macroscopic transfer of heat from the hot side to the cold side. Therefore, normal scattering does not create thermal resistance. It doesn't act as a brake on the system. It's just traffic smoothly merging lanes on a highway.
Okay, so end processes are relatively harmless. They happen constantly, but they don't stop the heat flow. But then we have the second type of collision, the U process. And reading through the physics notes, this seems to be the ultimate villain of the story if you were trying to conduct heat.
The U process is everything. It is the core of thermal resistance in nonmetals. The U stands for Umklapp scattering.
Umklapp. It's a great word. What does it actually mean?
It's a German word introduced by the physicist Rudolf Peierls in 1929 when he was first mapping out these quantum lattice dynamics. Clap literally translates to flipping over. And that translation is the perfect visual for the physics of what is occurring.
Wait, why would a wave flip over? If two ripples hit each other in a pond, they don't suddenly shoot backward.
Because the pond is a continuous medium. A crystal lattice is not continuous. This is where the quantum mechanics really come into play. A lattice is a fixed, rigid, periodically repeating grid of discrete atoms.
Okay, discrete atoms.
The atoms have highly specific quantized distances between them. Because the grid is discrete, there is a fundamental mathematical limit to how much momentum a wave can carry before it becomes physically impossible for the grid to support it. Physicists refer to these limits as the boundaries of the Brillouin zone.
The Brillouin zone.
Yeah.
So you can't just have an infinitely short, instantly energetic wave, because eventually the wavelength becomes smaller than the distance between the actual atoms themselves. The medium simply can't physically bend that way.
You've nailed it. There is an invisible boundary, a Bragg plane dictated by the geometry of the crystal. If the atomic vibrations, the phonons, get too energetic and two phonons collide, their combined momentum might try to exceed the maximum allowed momentum of the Brillouin zone.
And what happens then?
The combined wave essentially crashes hard against the structural geometric limits of the periodic grid.
So it hits a wall. But what does the lattice do in response?
The lattice recoils. The physics of the periodic boundary is so strict that the excess momentum is transferred entirely to the macrostructure of the crystal lattice itself, and the resulting phonon wave doesn't just deflect, it is violently ejected in the exact opposite direction. It flips over.
Oh, wow. So if I'm a package of heat energy, and I am desperately trying to travel from the left side of the crystal to the right, and I suffer an Umklapp collision, I am instantly rocketing back to the left. I am literally losing ground.
Yes. This is why the U process is the true culprit behind thermal resistance. It is the ultimate brake. Every single time an Umklapp process happens, heat energy gets pushed backward instead of flowing forward.
So it's actively fighting the flow.
Completely. The more U processes you have occurring in a material, the worse it is at conducting heat. The mean free path, our variable, shrinks dramatically because the phonon can only travel a tiny microscopic distance before it hits an Umklapp limit and gets flipped backward.
This is a massive revelation. N processes are just traffic merging. U processes are head-on collisions that magically teleport your car backward. So logically, if U processes are the brakes, then the winner of the heat conduction race is whoever can keep their foot off the brake pedal the longest. Whoever can avoid triggering these Umklapp collisions.
That is the secret to diamond supremacy. It lies entirely in its ability to avoid Umklapp scattering. And to understand how it achieves that, we need to introduce a magic number, a specific threshold called the Debye temperature.
Okay, what is the Debye temperature conceptually?
The Debye temperature, denoted as theta sub B, is a unique property of every solid material. Conceptually, it represents the specific temperature threshold at which the ambient thermal energy is high enough that all the possible vibrational modes of the crystal are activated.
Okay.
More importantly for our story, it's the temperature region where the atoms are jiggling violently enough that their phonons consistently have enough momentum to trigger those nasty reverse flipping Umklapp processes.
So below the Debye temperature, the vibrations are relatively calm, the phonons are crashing into each other, but the collisions are mostly gentle end processes. They don't have enough combined momentum to break the lattice limit and flip over.
Right. But as the physical temperature of the material rises, you are injecting more thermal energy. The atoms jiggle harder. The phonons carry more momentum.
Oh, man.
As you approach the Debye temperature, the collisions become increasingly violent, they hit that brilliantine zone boundary, and U processes start happening everywhere. The brakes are slammed to the floor.
This is where we can finally put copper and diamond head to head. Let's look at copper through this lens. Copper has phonons. What is the Debye temperature of copper's lattice?
The Debye temperature of copper is approximately 340 Kelvin.
Okay, let's ground that in reality. Normal room temperature, like the temperature of the room we are sitting in right now, is roughly 300 Kelvin, about 80 degrees Fahrenheit. So copper's Debye temperature of 340 Kelvin is just slightly above comfortable room temperature. What does that mean for the phonons trying to move through a copper wire right now sitting on my desk?
It means they are in absolute agony. Because room temperature 300 Kelvin is so incredibly close to the threshold of 340 Kelvin, the baseline ambient heat energy in the room is already enough to make the copper atoms vibrate wildly.
So they're already at the limit.
Exactly. They are constantly flirting with that momentum limit. This means that at room temperature, U processes are triggering constantly inside copper. The brakes are slamming on relentlessly. Wow. This is precisely why the phonon contribution to copper's heat conduction is a rounding error. Its lattice structure is a chaotic, impenetrable mess of unclapped scattering at everyday temperatures.
The copper lattice is basically a highway where half the cars are driving the wrong way, crashing into everyone else, flipping them backward. No wonder copper has to rely on the electron sea to do all the work. It has to use the brute force of 1 million delivery trucks to bypass the fact that its highway is a disaster zone.
The lattice is actively fighting the heat flow. Now let's turn our attention back to diamond.
I feel like the punchline here is going to be absurd. If copper is 340 Kelvin, what is the Debye temperature of diamond?
Because diamond is constructed of those incredibly light carbon atoms bound together by those universe-stiff covalent bonds, the lattice is insanely rigid. It refuses to bend.
Right.
Therefore, it requires a truly astronomical amount of ambient heat energy to make the atoms vibrate violently enough to trigger an unclap process. The Debye temperature of diamond is a massive 2,200 Kelvin.
2,200 Kelvin. That's nearly 2,000 degrees Celsius. That is hotter than molten lava. That's approaching the temperature of a rocket exhaust.
It is extreme. And here is the aha moment that completely solves our paradox. If diamond's threshold for slamming on the brakes is 2,200 Kelvin, what is happening to the phonons inside a diamond ring sitting on your desk at normal room temperature? 300 Kelvin.
Well, 300 Kelvin is practically absolute zero compared to a limit of 2,200 Kelvin. It is so far below the threshold, the atoms aren't vibrating violently at all relative to their limit. They are perfectly, rigidly calm.
Yes. At room temperature, a diamond is operating in a state of deep cryogenic freeze relative to its own Debye temperature. Because it is so far below the threshold, those high-energy phonons simply don't exist yet.
If they don't exist.
And if they don't exist, the U processes, the unclap scattering, the brakes are practically non-existent.
The brakes are entirely frozen, they're completely disabled.
They do not trigger. The thermal resistance of the lattice drops to nearly nothing.
Okay, let's visualize this final picture. We have our phonon wave injected into the diamond from a heat source. We already know from the first half of the equation that the wave is moving at 18,000 meters per second.
Yeah.
And now we realize that because the temperature is so incredibly low relative to the 2,200 Kelvin limit, there are almost zero U processes. There's nothing to flip the wave backward.
So what happens to our final variable, MESL, the mean free path?
It must stretch to infinity, or at least macroscopically huge distances. How far does the wave go before it crashes?
Because the brakes are frozen, the phonons in a diamond at room temperature face absolutely minimal thermal resistance from the lattice. The source material notes a specific phenomenon here. The phonon travels unimpeded for micrometers at a time.
Micrometers.
Now, to a human, a micrometer is tiny. But on an atomic scale, traversing a micrometer without a collision is an enormous, almost unimaginably vast distance. It means bypassing thousands upon thousands of atoms without a single meaningful disruption.
It's the equivalent of driving a car in a perfectly straight line for 10,000 miles without hitting a single pothole or needing to touch the steering wheel.
And because it travels so far and in such a perfectly straight line, physicists use a very specific term for it. They say the phonon travels ballistically.
Ballistically. like a bullet fired from a gun.
Or, to paint a more evocative picture, imagine a rocket moving through the deep, empty vacuum of interstellar space. There is no air resistance, no friction, no planetary bodies to crash into. The rocket fires its engine once, and then it just glides, flawlessly maintaining its massive speed over vast distances, completely unimpeded. That is what a heat wave does inside a diamond.
That is awe-inspiring. You look at a diamond on a piece of jewelry, and it just looks like a shiny inert rock. But at the microscopic level, it is a hyper-advanced frictionless highway for quantum vibration. It is moving energy ballistically.
It really is.
And this totally explains the math. You take our equation, kappa equals 1/3 c times v times L. You have an astronomically high velocity, v, because of the stiff bonds. And you multiply that by an astronomically long travel distance, L, because the umclap scattering is frozen out by the 2,200 Kelvin W temperature.
And the result.
You multiply those two massive numbers together, and you get a thermal conductivity of 2,000 watts per meter Kelvin, a number that leaves the brute force of copper completely in the dust.
It mathematically guarantees diamond supremacy at room temperature. But your deduction also implies a fascinating edge case. What would happen if you took that diamond and heated it up to 2,000 Kelvin?
Ooh. If I heat it up to 2,000 Kelvin, I'm approaching the Diddy temperature, which means the atoms are finally vibrating wildly enough to hit the Brillouin zone limits. The umclap scattering would turn on, the brakes would unfreeze.
Exactly. At incredibly high temperatures, diamond loses its superpower. The U processes start flipping the phonons backward, the mean free path collapses, and its thermal conductivity plummets.
That perfectly highlights how temperature-dependent these infrastructures are. This brings us to a perfect synthesis of everything we've discussed today. I want to step back and look at the overarching theme regarding these two political parties of heat transport, because there is almost a philosophical difference in how these two materials operate. It's a tale of two completely opposing evolutionary strategies in the world of material science.
It really is. It's mass versus perfection.
Let's look at the metal approach, the copper strategy. Based on the Drude-Sommerfeld models and the scattering dynamics, I would describe copper's method as pure, unadulterated brute force.
That's a good way to put it.
Copper doesn't have a clever, efficient system. It relies on sheer numbers and overwhelming volume. It sends out these massive, chaotic armies of free electrons, billions upon billions of them, and their journey is terrible.
They're constantly crashing.
Yeah, they suffer constant scattering. They crash into vibrating atoms. They slam into impurities. They get hit by the umclap brakes constantly because the lattice is too hot at room temperature. They bounce around chaotically like a microscopic pinball machine.
It's messy.
It's an ugly, messy, highly inefficient process on an individual particle level. But because there are so astronomically many of them, and they are inherently moving at the Fermi velocity, they batter their way to high conductivity.
It is the equivalent of trying to move a mountain by having 1 million people carry one handful of dirt at a time while constantly tripping over each other. It gets the job done quickly because of the sheer size of the workforce, but it is pure, unrefined chaos.
And then on the complete opposite end of the spectrum, we have the insulator approach, the diamond strategy. I would call this extreme refinement. Diamond has 0 electrons to rely on. It has no workforce. It cannot use brute force.
If it tried, it would just be an insulator.
Right. If it tried to use brute force, it would be a terrible conductor like plastic or wood. Instead, it went the other route. It built the universe's most perfect, rigid, flawlessly disciplined crystal grid.
By forging those incredibly stiff, lightweight carbon-to-carbon bonds.
Yes, and by doing so, by raising its deadly temperature so astronomically high, it completely disabled the brakes. It eliminated the umclap scattering. It took the chaotic, crash-filled environment of the crystal lattice and smoothed it out into absolute quantum perfection.
And because the environment is perfect.
Because the environment is perfect, it allows a pure wave of energy, the phonon, to glide through it flawlessly. It's not 1 million delivery trucks crashing off-road. It is a single, sleek, high-speed bullet train operating on an entirely empty, friction-free, perfectly straight track. Doesn't need 1 million workers, it just needs one perfect path. And that elegant refinement ends up being 5 times faster than the brute force of the electron sea.
It is a profound realization about how nature solves the problem of energy transfer. And the source material touches on this beautifully. When researchers in solid-state physics look at raw lab data when they measure electronic conduction or plot out curves for lattice vibrations, They aren't just seeing abstract numbers on a screen.
No, they're seeing the whole story.
They are seeing these epic, microscopic dramas play out in real time. Every data point on a graph of thermal resistance is a record of a collision. It is a record of an umclap process flipping a wave backward. The math is just the language we use to describe this incredible, invisible theater of physics happening right under our fingertips.
What an incredible journey today. We started with a simple, everyday sensation of touching cold metal and feeling the heat leave your hand. We dove into that metal and swam in the sea of free electrons, discovering the elegant Wiedemann-Franz law that proves electrons are the delivery trucks for both heat and electricity.
We covered a lot of ground.
We really did. We then left the electrons behind entirely, crossing over into the weird quantum world of insulators. We learned how heat can move without particles, manifesting as a stadium wave of jiggling atoms called a phonon. And finally, we witnessed the ultimate triumph of dynamite. We saw how its incredibly stiff, lightweight atomic bonds create a speed of sound that is mind-bogglingly fast, and how that same rigid structure pushes its Debbie temperature to 2,200 Kelvin, completely freezing out the unclap scattering breaks.
Our goal today was to translate these complex laboratory concepts into something deeply understandable, to give you a surprising new perspective on the material world. Now, you know exactly why materials conduct heat differently, all the way down to the quantum level of lattice vibrations and electron scattering.
You are officially armed with the knowledge of the hidden infrastructures of reality. So I want to leave you with a final, provocative thought to mull over. Tomorrow morning, when you wake up, you are going to interact with hundreds of solid objects. You will hold a metal spoon to stir your coffee. You will wrap your hands around a thick ceramic mug. You might touch a piece of jewelry, a glass window, or the plastic steering wheel of your car.
Heat is going to be moving everywhere.
Exactly. Every single time you touch one of those objects, heat is going to move. But next time, don't just feel the temperature. Stop for a second and think about what is secretly happening against your skin, right at the atomic boundary. Close your eyes and ask yourself, what infrastructure am I touching right now? Am I feeling the chaotic microscopic crashes of a trillion brute force electrons tearing the heat away from my hand? Or am I interacting with a perfectly tuned, invisible crystal lattice, sending a microscopic symphony of unbreakable waves deep into the heart of the object? We think of solid objects as dead, unmoving things. But the truth is, the world of the solids is anything but still.